Hello. Statistical models can be generated to make predictions or to facilitate understanding about the world. Here we're going to look at model selection primarily in terms of making predictions. Well, who makes predictions? Well, biologists might make predictions, for example, polar bear weight based on their claw size or snout length. However, we may wish to make predictions about the world population sometime in the future, or indeed climate and how climate might change over the coming decades. Companies around the world also use predictive modeling to understand customer behavior and how and what they will be choosing in the future. Now, in this short lesson, we're going to be looking at a particular form of model selection. That is, a form of model selection based on polynomial regression. Here we have some data relating the concentration of cesium to the depth of soil. Now, the data look approximately linear, and we could decide to fit a simple linear regression model. And that's what the model might look like. It's a simple model with a gradient and an intercept describing that relationship between the response variable and the predictor. However, data of this form could be very well approximated using a polynomial, that is, a relationship between y, a response, and a predictor x, but also x squared, and perhaps even x cubed, x to the 4 and x to the 5. That's what we mean by a polynomial. Many different terms of x raised to different powers. So we could choose instead to fit a model like this, which actually hugs the data really very closely indeed. That of course would be a more complicated model, a model involving perhaps terms in x squared, x cubed, x to the 4th, and perhaps even x to the 5th. And the question is, should we always be choosing complicated models over simple models when trying to develop the very best predictive model? And the short answer is no, because when we fit extremely complicated models to data, we could be overfitting our model to the data. What do we mean by overfitting? Well, it arises when we attempt to explain the noise as well as a signal in any given relationship. For example, we might fit a high order polynomial to this type of graph here. Of course, we're explaining much of the relationship, but in overreaching ourselves, we are trying to explain the noise as well as the signal. So, the exact fit is not necessarily the best fit, because in overfitting our model, we are actually losing predictive power rather than gaining it. The most predictive power will arise when we can capture the essence of the relationship without explaining the noise in that relationship. Let's have a look at the process of fitting polynomial models to data and how we might go about choosing the most appropriate polynomial to represent those data. Here are some data that have been made up, and here I am simply reading them in and plotting the x and y relationship. Now, when we fit polynomial models, we may wish to fit models with not just x, but x squared, and maybe even x cubed or x to the 4th. So this is what I'm doing here. I'm defining new variables on the basis of previous variables. So we have all the x values in that vector here squared and here cubed. And then of course what I'll be doing ultimately is fitting a variety of models. Here's the model 1, that's the simple linear model. The model 2 is a quadratic model, and the model 3 in this case is a cubic model. Notice that when I fit the cubic model, I also include the model for x squared, and likewise x, and when I fit the x squared model, I also include the x. Now that is because we are respecting the hierarchies in the model fitting process. Okay. Now, I'll show you how to actually fit these various models and draw them in the next RStudio practice. But for now, let us assume that we fitted a linear regression model to our data, and you'll notice that the multiple r squared is about 70%, and these are the best estimates for the parameters for the intercept and the gradient. However, when we fit the quadratic model, you'll notice first of all that we increase our r squared value. That's the proportion of the variability in terms of sums of squares that can be explained by the fitted model. And here we change slightly our intercept, and we have different parameters for the x and x squared coefficients. And here is the relationship of that relationship between y and x expressed in terms of the quadratic fitted model. And here is the cubic fitted model, and you'll notice that the multiple r squared has actually gone up, and here are the estimates of the parameters that we have estimated through fitting this model to our data. Should we be using r squared as a criteria for deciding when to stop fitting a more complicated model? Well, no. In the context of polynomial regression, a higher order polynomial will always explain more of the variance than a lower order model. And that is because the higher order model will collapse to a simpler model by setting one of the terms to 0. So the best fit was for the highest order equation. But that's always to be expected. Cubic reduces to the quadratic as a special case. Here is the key question that we should be asking. Does the addition of new terms explain significantly more of the underlying variability in y? To ask this type of question, we need a type 1 sum of squares. So when adding new terms in which the predictors are highly correlated, then clearly it's appropriate to consider type 1 sequential sums of squares, because through that collinearity they might otherwise mask one another's effects. With the type 1 sum of squares, it allows us to empirically build a model until extra terms explain little additional variance in our response variable y. So let's see how that works. Here is the linear model that's been fitted to our data, and we can simply call up ANOVA for model 1, which was generated by fitting that general linear model. And here is the analysis of variance table. What this tells us is that x explains significant variability in that response variable y. So all is good. Now let's have a look at the more complicated quadratic model that we fitted. Here I'm asking for the analysis of variance breakdown with model 2, and this is with a type 1 sum of squares by default. And here what we can see is, first of all, x explains significant variability in y, but then also x squared explains significant variability in y above and beyond that explained by x. So x squared explains significant variability in y above and beyond what x explains. So that justifies the extra term, the x squared term in that model. In effect, it's taken some of the curvature in that relationship. Now we can ask about the cubic model that we have fitted. There's the graph of it, and here is the analysis of variance. You'll remember that we're using type 1 sum of squares, and so what we can see here is x is highly significant, x squared is highly significant once we take into account the effect of x, but x cubed is not significant once you take into account the role of x and x squared. So x cubed does not explain significant variability in y above and beyond x and x squared. What about the residual plots? Well, looking at the residual plots for those three separate models suggests that there might be a slight issue with that linear relationship that we had assumed. And that is because all of these residuals appear negative. Most of these appear positive, and here they're somewhat split. So what we have are slight issues with the lack of independence of the residuals in that linear fit due to nonlinearity. But here with the quadratic and cubic, the residuals look pretty well distributed. You can't predict the size or sign of any residual by looking at the neighbor residuals. So let's apply some common sense criteria in selecting the most appropriate polynomial model in this case. There's fewer terms in the quadratic, so it avoids overfitting. The cubic term does not explain a significant amount of residual variability after the terms of x and x squared were accounted for. And the quadratic and cubic appear equally appropriate with respect to those residuals. So everything points in this case to using the quadratic model as a predictor of the change in y with a change in x. Thank you for listening to this R-Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.